All right. So let me know when to start. Okay. So today we're going to be talking about how are we going to be using OpenMP in different applications and what are their needs and how we're basically addressing them in the context of the ECP exascale computing project and how we are working with the rest of the community on doing this. We like OpenMP because it's a de facto standard for many vendors that will allow us to run applications on multiple architectures. We're interested in working in a standard that could run on multiple leadership class computing systems, especially in the Department of Energy. And as a bigger standard, it's a great place to work, but also has challenges. And we need to understand what's the best approach to express the needs of applications in the context of to the community. As we see in the top 500 list for the last several years, we have seen that architectures are significantly changing in the context of the top 500 list, where we initially had applications that were targeting in the early 2000s multi-core architectures, but as we evolve, lately we're moving more in the context of accelerator type of architectures. And as we see that evolution, we also see that OpenMP has been kind of respond to that sort of trend. And in the latest, the latest result is like we have support for example, for accelerators and initially in the earlies, in the mid-2000s, we have support for tasking, and then before that, we support for multi-cores. So this has a project that has evolved over time, and it comes in response of the type of architectures that we are supporting. For us in Oak Ridge, we definitely like the idea of having a portable programming model, and we see that trend also in our architectures. In 2008, we have Jaguar, who was a multi-core architecture, and then in 2012, we have a computer called Titan that was based on GPUs, and that was a big gap for us, and we wanted a directive-based programming model to target that machine. And then in 2017, we had Summit, and 2021, now we have Frontier, and all of these architectures are based on accelerators or GPUs, and we want to use OpenMP to program them. One of the challenges is that a lot of the codes that are running in these machines come from different programming models, and the traditional ones are Fortran and C++, and we see that, for example, the ratio between the what is basically generating the cycles in these machines come from these two base languages, and we need to make sure that these languages can also run in the accelerator or also in the multi-cores. So when we look at directive-based programming approaches, we see that we need to have something that we can easily do that, especially in the context of Fortran. When we look at how we are today, we are seeing that directives is being used, especially in the past, but we are basically, the growth is in the context of directives that has target specific GPUs, but we see also a growth in OpenMP. And as we are making those directives more available, we're also generating more cycles in the machine that basically are doing that and going in the direction of a standard that can run some multiple architectures. So why do we need OpenMP? Basically, the applications need it because they need a programming layer to program the different types of memories available in the node. They need an API for dealing with data movement, data abstractions, basically directives that will help to orchestrate the work between the host and the devices, and how they can coordinate and distribute the work between them. And we have several applications that have been looking at using OpenMP offload and for accelerators, and there are E3SM, LQCD, Candle, QMCPack, and NWChem. And all of them have expressed their need to use OpenMP. But on the other hand, we have a lot of codes that are written in other languages, especially Cocos and Raja, which basically use OpenMP, can use OpenMP in a different way. Currently, OpenMP can be used directly in the applications, like a Fortran code that you basically insert those directives there, or it can be used indirectly through a framework like Cocos or Raja, and that will help us to generate OpenMP and run it on multiple architectures. On the other hand, we have other standards that are also emerging, especially in the context of AMD, we see HIP, and in the context of NVIDIA, we see CUDA, and ensuring that OpenMP interoperates with these languages is also very important. And also we see the evolution of using also other directives. So we have to figure out how we can do this in a way that is interoperable and that the users can use it in their applications. So one of the additions in OpenMP 4.0 and now in 4.5 and 5.0 is the use of the target directive, where it allows us to offload computations to the devices, to the GPUs, and that has helped a lot in the adoption of how we're going to be running OpenMP in these new systems. We basically, the idea is that we see the accelerator as a new OpenMP environment where we can offload data and computations, and then we can later on synchronize with the host or the initial device that is spawning those computations, and then we can use directives to coordinate the data movement and the work. On the other hand, we can also use OpenMP new features that we have to program multiple devices and also coordinate the work with the hosts by using some of the capabilities we have in OpenMP with tasking, where we can, and dependencies, where we can basically offload computations to the host and also to multiple devices through the use of dependencies. And that also helps us to orchestrate some of the work that we need to orchestrate what the applications are using on multiple devices. So how those applications are using OpenMP? Currently, OpenMP is being used in several key applications, and some of the areas that they're trying to look is a performance portable programming model. So for example, we have one application called QMC Pack that is trying to run on multi-core, but also in different accelerators, and using OpenMP is allowing them to do that. But one of the challenges that they see is not only the portability of the programming model, but also how we can make it performance portable. And it looks to me that right now, one of the challenges that we see, for example, in OpenMP 4.5 is that do we really want to write code that is good for the multi-core, or do we want to write code that is good for the accelerator? And how do we handle those two things? And ideally, we want to have like one source code that can be targeted in both architectures. And what we see is that depending on the problem sizes that they are trying to run, for example, the CPU version is doing a good job, but if the program size is bigger enough, for example, the accelerator version is better. So basically, the portability aspect is not only, it's also dependent on the problem size that we're running and also the target architectures that we're using. So, so the other need that we have is that all these applications are using libraries and they need to interoperate with OpenMP. And we also need to have a very efficient implementations of the offload directives, especially because many of these codes have very small kernels, and we need to make sure that they are offloading computations to the devices quickly with little overheads. And that's an important aspect that we need to target in the context of OpenMP. And then other challenges are issues with the tasking. Basically, how can we do advanced tasking to coordinate the work between the multi-cores and the accelerators? The other challenge that we see in OpenMP is that in applications is that a lot of these applications are using very complex data structures that they need to move back and forth from the host to the device, and we need to make sure that those are those transfers are efficient and we can express it in the language. And currently, for example, we have analyzed applications, look about how many of them have complex data structures or structures that have pointers or to other memories, and how do we handle those back and forth between the host and the device. And we call that the deep copy problem. And in OpenMP 5.0, we came up with a solution to do that using custom mappers, where we basically can move a complex data structure like a vector of a vector from the host to the device. And we can basically specify it in a way that OpenMP can understand that and take care of the data movement. So that is one of the challenges that we see when we're moving codes to accelerators, is basically how can we solve the issue of data mapping between the host and the devices. And this is one thing that we are addressing in the context of OpenMP 5.0. The other challenge is that we have this application that that is writing codes for the CPU, but also may have a different strategy for the GPU. And by finding different levels of parallelisms in the code or performing some code transformations, and if we want to create one single version of the code or find a way to make this more manageable, we definitely need to explore new type of directives. And in OpenMP 5.0, we have the meta directive that will help us to change some of the behaviors of the directives, and depending on the context where they're being invoked. We also have a capability of creating variants, and loop transformation capabilities are also being discussed in the standard. So that will help to manage the versions of the codes between multiple devices, including the CPU and the GPU. Tuning is very important, especially in the context of schedules and loop transformations for the GPU kernels or for the target kernels. And we need to have better mechanisms to find ways to tune the codes so that we can get the best performance possible. In OpenMP 5.0, we have new capabilities that is going to start addressing this. One are based on the loop directive that we added in OpenMP 5.0, where we leave the capability to the compiler to pick what's the best implementations and the schedules that we need to do that. And we also have the capability of adding these custom mappers that I just talked about before, and also the support for shared memory, for unified memory, which is also going to reduce the burden of moving codes from the host to the device. So this is just an example of how these directives are going to look like in the codes, where we can just express. Basically, initially we could have 3 versions of a type of parallelism that we want to express in a loop. But with the directive, we will have one where we basically let the compiler pick what's the best implementation, and that will allow the code to be more portable, and it could generate a parallelism inside a GPU or a device, or it could be something, it could generate a task or a SIMD type of parallelism, and that's an important feature that we want to support. But to do this, we need very important analysis the compiler needs to do. Basically, needs to focus on cost models, where basically the compiler needs to decide what's the best strategy to do that, and what type of parallelization it needs to do to generate the efficient code. And that will definitely help in the context of performance portability. So one of what the community is really asking in the context of directives for OpenMP is that we have quality implementations and full standard supports across architectures, interoperability with other programming models. Tasking is important in OpenMP to orchestrate the work across accelerators and the network and the multi-cores, consistent implementations across compilers and architectures, so that all the compilers are basically translating OpenMP in a similar way, so that we reduce the cost of performance portability across compilers, make sure that that works, and then look at is the transition between OpenMP and OpenACC in the context of having these models available in compilers will help to move from one to the other, so that the user can decide what's the best approach that they need to support what they need in their code, with the idea that with OpenMP having more implementations in different architectures will be helpful for them in the long term. So, and then the idea of having common runtime APIs when different compilers can link together and being able to interoperate is also very important and expressed by that. And this is a list of things that we have identified by applications and the use cases that they have that they need in the context of OpenMP. And we're kind of like working on with the standard communities so that we address them, and many of them are being addressed already by OpenMP 5.0. And we're just kind of like making sure that they are implemented and correctly in the compilers and become more available. And these are some of the things that we definitely need to continue working and supporting. And one of the things that we definitely, we still need to look forward in the future is how do we support better the parallelism in the device, especially how much do we expose for the streams in the GPUs, because currently that's an area that is a little bit challenging for the applications. And these are some of the lists that we wanted to do that. And we're basically working with many applications where we're basically parallelizing with OpenMP offload to make sure that we can test those ideas and provide examples to the community so that they can see how it's being used. And currently, the majority of the codes have OpenMP in their CPUs, but very few are starting to adopt it in the GPUs, but that's kind of like growing. And this is a suite that is available by the ECP project that has these types of implementations. And in addition to that, we're also working with the spec community to create benchmarks that have OpenMP offload in those benchmarks as an example of how this can be used, and as an example of best practices for applications. And with that, I finish my talk. Are there any questions?